Have you ever sat back and considered how one area of your life could possibly affect or impact another area of your life? So, for example, maybe you've started to think about your sleep before and you say, hey, I wonder how much sleep I get at night affects my focus or my mood the very next day. Or maybe you've thought about exercise and working out. Maybe you've thought, hey, I wonder how much time I spend exercising. How does that affect my fitness, my health? Maybe you felt the same way about food. Maybe you think about, hey, how do the things that I eat or I drink, how does that affect my mood or my attitude throughout the day? Well, I hope you think about these things. These are good, critical questions that you can ask, and there's really no limit to the types of questions that you can ask when you start looking how one thing impacts another. Now, this is an enormous part of algebra. In algebra, we call this a relation. A relation is technically the definition is it's a set or collection of ordered pairs. But the way I like to think of it is this. Anytime you take one set of numbers and pair them up with another second set of numbers, that forms what's called a relation. And in a relation, you're really asking the question, how does set X relate to set Y? So I made up a scenario here. Suppose I had a class last year of 10 students, and here's one set. One set I had on this class was the number of absences, the number of times that a student was absent from the class. And then over here in this column, I have a second set of data. It was their grade. What grade did they end up getting for the first quarter? Well, I want to study if there's a relation between these two. I've set up a relation. I want to study kind of the cause and effect between these two things. Is there a cause and effect? Is there a correlation? But when we set this up, this is in math class, this is called a relation. How does X relate to Y? Now, there's four main ways you can display a relation in math class. Now, number one is very boring. It's just simply a list. Here I've written out all of these ordered pairs as a set. Okay, so that's one way to do it, kind of a dull way to do it. Number two is what you already saw here, okay? A second way to show a relation in math class is through the table, the good old XY table. That's what we started with. Now, the third way to show a relation is kind of bizarre. It's kind of odd. It's called a mapping. All right, I don't know if you've ever seen this before, but a mapping looks like this. A mapping, you say, okay, somebody that has 0 absences maps to either 90. We had one with a 90. We had another student with 0 absences that got a 95. Over here, we had another student with 0 absences that got an 85. And a mapping is we draw these arrows to show the pairings. Okay, students with 1 absences, one student had a 75, another had a 90. Okay, you get the idea. So there you go. I finished off that mapping. I always thought mappings were kind of bizarre, and the larger your data set too, like the more confusing it kind of gets. But that's what a mapping is. But let's be honest. When it comes to showing a relation, the most visual, and I think it depends on the situation, but in a lot of times the most effective way to show a relation is on a graph. The beautiful thing of a graph is a graph can show a lot of information in just one glance. There's a saying that says a picture is worth 1,000 words. Well, I think the same is true of a graph. On a graph, I think it's easy to see the relation between number of absences and the grade, and you can look here and say, oh, there's a downward trend. It doesn't make like a perfect line or anything, but based on these 10 students, I can see kind of a downward trend, how the more absences you have, the lower your grade would get. So our next focus now is going to be on these two vocabulary words, domain and range. Domain is, the definition is the set of all x values in a relation, whereas the range is the set of all y values in a relation. Now I want to point something out. This graph right here, this graph is called a discrete graph because you'll notice all of these points are separate. Okay, there's no line connecting these points. Everything is separate. And part of that is because you can't have, I don't denote absences as like a quarter absence or a half of an absence or like 2 1/4 absences or 2.9 absences. Okay, the way I record absences, you either have 0 or 1 or 2 or 3 or 4. There's no kind of partial in-between amounts that you can get. And so that really separates out these points. And the other reason this graph is discrete is you're talking about individual people. Okay, so you have these 10 individual people. They're all going to show up as their own point. Now, to state the domain, if you ever have a graph that's discrete and you want to state the domain, really what you can do is just make a list. We're going to go from the left of our graph to the right. And for every point that we see, we're going to list the x value that we see. All three of these points have an x value of 0. Try that again. All three of these points have an x coordinate of 1. Both of these points have an x coordinate of 2. This point has an x coordinate of 3, and this point has an x coordinate of 4. So here's my domain. Now, you only write each x value once, okay? So even though 3 students had perfect attendance, I'm only going to write the 0 one time. I'd say the domain of this relation is 0, 1, 2, 3, and 4. I can write that as a list. Now for the range, I'm going to consider the y values. When I go to write down the range of a relation, this time I want to go from the lowest point to the highest. If I'm looking at a discrete graph, I want to find my lowest point, which is here at 55. And then I'm going to start working my way up. Now, both of these points have a y value of 65. Both of these points have a y value of 75. This point has a y value of 80. Here's an 85, 2 90s, and a 95. So 85, I'm only going to write the 90 once, of course, even though there's 2 of them. Okay, here is my range. These are all the grades, all the y values that students had in this class. Now, the last vocabulary word we're going to look at today is the idea of a function. So a function is a type of relation where all elements of the range pair with exactly one element of the domain. And another kind of easy way to think about this is in a function, you don't have any repeating x's. So I want to ask myself the question, is this relation a function? And the answer is that it is not a function, because you have repeating x values. You have, for example, you had 3 students that had 0 absences. Okay, so 0 repeated. You had 3 students that had 1 absence. You had 2 students that had 2 absences. These x values repeat, and so this is not a function. Now, on a graph, what you can do is you can look to see if there's ever points stacked on top of each other. Another way to think of this, points stacked on top of each other makes it not a function, because that means you're going to have repeating x values. So if you're looking at a table, it's really easy to see repeating x values. Here's a 2 and here's a 2. If you're looking at a mapping, I think it's easy to see you have all these arrows coming away from a number. But on a graph, look for points stacked on top of each other. Now, I will make out a point real quick. It doesn't matter if you have any repeating y values. Like here, a grade of 75, it shows up twice. That's actually allowed in a function. You can have repeating y values, but you are not allowed to have repeating x values stacked on top of each other in a function. All right. Now, the last type of graph that we want to look at here is a graph where the points are connected. So here's the last graph we'll look at. This graph is called the monthly cost of a Google Fi phone plan. Now you'll notice here there's no separate points on this graph. This graph is a solid line, and we call a graph like this, we call this a continuous graph. Now, when it comes to finding the domain of a continuous graph, it's actually kind of tricky, because the problem with the continuous graph, a continuous graph is really a collection of many small points. So if you ever ask yourself the question, hey, how many points are on this line, on this continuous graph? Well, the answer is there's infinitely many, okay? This line is really a collection. Imagine me drawing all these infinitely tiny little points along this line. Okay, there's hundreds of points, thousands, tens of thousands, millions. infinitely many little points that you could draw on this line. And a continuous line is just a collection of all of these points. So imagine now trying to write a domain, okay? Imagine trying to make a list where you write, every single little point that could possibly exist. Not only all the whole numbers, but all the little decimals in between. Okay, it would take forever. It's an infinitely large list. You can't, a continuous graph, you cannot write your domain as just a list. It's going to be impossible because of how large it is. So this is a great time to use what's called interval notation. With interval notation, what we do is we find the leftmost point of our continuous graph, and then we find the rightmost point on our continuous graph, and we separate them with a comma. Now my leftmost point of this graph is over here. It has an x-coordinate of 0. Now the rightmost point of my graph right here is actually an arrow. And an arrow, we say, goes to infinity. Now I'm going to draw the infinity symbol here. And then what we do is with any number that we have, we're going to put it in a square bracket. And then if we have an infinity symbol, we're going to put it in a parentheses. What this means is that the domain is all of the numbers you can possibly imagine between 0 and infinity. Okay, now notice you don't have any numbers here to the left of the 0. The leftmost point you can have is a 0. We put it in a square bracket. And then the rightmost point is an arrow. We're going to put an infinity symbol for this. Now, the range is going to be similar, but for the range, we're going to find the lowest point that we can find on the continuous graph, put a comma, and then we're going to put the highest point that we can find on the graph. Now let me change colors here. I'll do this one in red. The lowest point on this graph, it's still this point right here, but now we're looking at its y value. It has a y value of $15. The lowest y value on this graph is 15. Now, since it's a normal number, I'm going to put it in a square bracket. But again, my highest point is, again, an arrow. And so with an arrow, I put infinity. Here I'm saying that the range of this graph is every point you can possibly imagine between 15 and infinity. And not only are we just talking about the whole numbers here, like 16, 17, 18, we're also talking about all the possible decimals you could have in between as well. It could be like 15.01, 15.02. Now, as we look at this graph and ask, is it a function, we really want to ask, does the graph ever bend over top of itself? Does the graph, do any of the points ever stack on top of themselves on this graph? And they do not, okay? This graph, none of the points are stacked on top of themselves. We say, yes, this is a function. The graph never goes on top of itself. Now, let me show you real quick an example of what would not be a function. If you ever had a graph that did something like this, okay, a graph like this would be not a function if it ever looked like this. But with a graph that, as long as the graph never bends over top of itself, then yes, that is a function. I would like to go over a couple of your problems on your online quiz. Here is question number 1, just to help you get started. So we need to realize this is a discrete graph. All these points are separate. So my domain is just simply going to be a list. So I look at my x values. These points have an x value of -5. This has an x value -2. And these have a 1. I need -5, -2. Oh, I'm sorry. These points have an x value of 2. So -5, -2, and these points are +2. Now for the range, I'm going to look at the y values. These points down here at the bottom have a y value of -4. These points have a y value of 1. This point has a y value of 3. -4, 1, and 3 is my answer. Now, is this a function? No, it is not. Notice how these points are stacked on top of each other. They share the same x value. And these points stacked on top of each other, they share the same x value. Not a function. Okay, let's scroll down to, let's scroll down. Let's actually do, let's do question 8 here. Now, question 8, realize, is a continuous graph. So with a continuous graph, I'm going to show my answers in interval notation. So for domain, I find my leftmost point. My leftmost point is an arrow. Now, if an arrow goes to the left, that's actually called negative infinity. Now, my rightmost point is an actual point. It has an x-coordinate of 3. My domain is going to be all the points from negative infinity to positive 3. Now, for the range, I want to find my lowest point, which is down here. It has a y value of negative 3. And my highest point, which is the arrow, we call that positive infinity. This is going to go from negative 3 to infinity. And this is not a function because the line zigzags over top of itself. It bends back over top of itself, not a function. And the last thing I want to point out here, if you ever have a problem where you have arrows on both ends, so let's look at the range of this function. Here my lowest point is an arrow, and my highest point is also an arrow. So technically you could say that this is from negative infinity to positive infinity, but the symbol that we use for this, what we say is all real numbers. If you ever have a graph that goes from negative infinity to positive infinity, a continuous graph, you would call that all real numbers. I wish you the best on this assignment. Take care.